Hello everyone. Welcome back to the second video of the Calculus for Deep Learning video series. The following few videos will cover essential nomenclature and relationships that we should keep in mind while coding deep learning algorithms. The information might feel quite overwhelming and give an impression that we are mugging up many unwanted mathematical formulas and relations. However, that is far from the truth. We make these videos hoping the viewers will write down these critical relations and refer to them when we code deep learning algorithms, and eventually the concepts will start to make sense. We know everywhere on the internet, we are told, that we do not need too much calculus when doing deep learning. Some fundamental understanding can help us leverage the mathematical frameworks already available in our development tools. However, I'm sure many of us are never satisfied until we know the concepts inside out. That is why we have decided to go as deep in the subject as possible and strengthen our core concepts while simultaneously applying them to different problem statements. I hope everyone will stick around till the very end to discover how fantastic calculus is, and that building the concepts ground up, we will be amazed by our skill set. Let us start by defining the notation we will be using in the following successive videos. Matrix will be denoted with a bold capital A. Matrix indexed for some purposes will be denoted with either A subscript ij, A subscript I, or A superscript ij. A raised to the power of n will have two representations. Either it will be a matrix indexed for some purpose, or it will be the nth power of a square matrix. A raised to the power of -1 will be the inverse of the matrix A. A raised to the power of plus will be the pseudo inverse of the matrix A. A raised to the power of half will be the square root of the matrix. In parentheses, matrix A subscript ij will be the I, jth entry of the matrix A, or A subscript I, j will also represent the I, jth entry of matrix A. Square bracket A subscript ij will be the ij submatrix, that is, we're removing the ith row and jth column from the given matrix, and the resultant matrix will be represented in this notation. Small letter A bold vector denotes column-wise vector. Small letter bold A with subscript I denotes vector which has been indexed for some purpose. Small letter A with subscript I denotes the ith element of the vector A, and A represents some scalar value. Determinant of A will be represented as det of A. Trace of the matrix A will be represented as tr of A. Diagonal matrix will be represented as diag of A. Eigenvalue of the matrix will be represented as eig of A. Vector version of the matrix will be represented as vec of A. Supremum of a set will be represented as sup. Matrix norm will be represented with two vertical bars with the on square matrix A. Transposed matrix will be represented with A raised to the power of t. The inverse transpose of a matrix will be represented with A raised to the power of negative t. A raised to the power of asterisk will represent complex conjugated matrix. A raised to the power of h represents transposed and complex conjugated matrix, also called as Herminian or Hermitian, either way. A dot product B is referred to as element-wise product, or also called as Adamar product. A cross product B is called as Kronecker product. 0, it will be representing the null matrix. I will represent the identity matrix. J raised to the power of ij represents single entity matrix 1 at I and j, and rest everywhere else it has a 0. Summation represents a positive definite matrix, and reverse V represents a diagonal matrix. Some basic relations that we have to keep in mind. Here A and B are two matrices, so matrix A multiplied by matrix B raised to the power of -1 equals inverse of matrix B multiplied with inverse of matrix A. Similarly, if we take multiple matrices A, B, C, D, E, F until whatever number we want, raised to the power of -1 is commutative, so we are going to multiply them in the reverse order, swap them, and then multiply the inverse of individual matrices. So basically it is all the entries from the end till inverse of matrix C multiplied by inverse of matrix B multiplied by inverse of matrix A. Similarly, matrix A raised to the power of t, and then when the whole thing is with respect to -1, we can bring in the -1 inside. So basically we are doing an inverse of matrix A and then transposing it further. Similarly, A plus B whole transpose, we can transpose individually these matrices and then add them together. So basically here we can see on the right hand side, A has been transposed plus B has been transposed, and then we can add them together. Similarly, A multiplied by B raised to the power of t is again commutative. So this becomes transpose of matrix B multiplied by transpose of matrix A. Similarly, A, B, C until some n number of matrices, everything raised to the power of t equals, it's again commutative. So all the entries will be transposed in the reverse order, and then C times, the transpose of C multiplied by the transpose of B multiplied by the transpose of A. Similarly, A raised to the power of Hermitian, and the whole thing is with -1 equals A. You bring in the -1 inside and take the Hermitian outside. Either way, the pronunciation is fine. I'd like to pronounce it as Hermitian. A times B raised to the power of H equals B raised to the power of H times A raised to the power of H. Similarly, A, B, C until some n number of matrices, everything is raised to the power of H. Then again we are doing a commutative association here. So we are multiplying the Hermitian C with Hermitian of B with Hermitian of A. Next, some important notations for trace. Trace of A equals summation of all the diagonal entries. Trace of A also equals summation of eigenvalue of A. Trace of A equals trace of A transpose. Trace of A times B equals trace of B times A. Trace of A plus B equals trace of A plus trace of B. And trace of ABC equals trace of BCA, which equals trace of CAB. Similarly, A transpose A equals trace of A times transpose of A. Let's suppose we have A as an n multiplied n matrix, so it is a square matrix. Determinant of A equals the product of all the diagonal entries. Determinant of C times A, you can bring in the C outside. This equals C raised to the power of n times determinant of A. Determinant of A transpose equals determinant of A. Determinant of A times B equals determinant of A multiplied determinant of B. Similarly, determinant of A raised to the power of -1, which is inverse of A, equals 1 upon determinant of A. Determinant of A raised to the power of n equals determinant of A. You first find and then take the whole expression to the nth power. Determinant of I plus U raised to the U times transpose of V equals 1 plus transpose of U times V. For n equals 2, determinant of I plus A equals 1 plus determinant of A plus trace of A. And for n equals 3, determinant of I plus A equals 1 plus determinant of A plus trace of A plus half of trace A raised to the power of 2 minus half of trace A. You square it first and then find the trace. And in this case, you first find the trace and then square that expression. That's the difference between these two. Okay. Important notation and nomenclature for a 2 cross 2 matrix. So some important things that you can keep in mind when you have a square matrix with 2 rows and 2 columns. So the determinant and trace, determinant becomes you're going to cross multiply. So it will be A11 times A22 minus A12 times A21. Trace will become the addition of all the diagonal entries. So it will be A11 plus A22. Eigenvalues will be nothing but quadratic formula. So it will be lambda square minus lambda times trace of A plus determinant of A, which will be equated with a 0. And the eigenvalues will be trace of A plus under root of trace of A whole squared minus 4 times of determinant of A upon 2, and lambda 2 will be equal to trace of A minus under root of trace of A whole square minus 4 times determinant of A upon 2. Lambda 1 plus lambda 2 equals trace of A, and lambda 1 times lambda 2 equals determinant of A. And the inverse of A will be represented by 1 upon determinant of A. What you do is you interchange the diagonal entries. So A22 comes here and A11 comes here. We've interchanged their positions and then we add a negative sign to the other diagonal entries. So it'll be a negative of a12 and negative of a21. So this is pretty much it for this session. Too many relations, and in the next successive videos we'll still continue discussing some important relations, and then eventually we will start solving questions where we will be applying all these relations. So it'll all start to make sense, hopefully. Yeah. So thank you so much. If you have any questions, feel free to put them down in the comment section. Yeah. Thank you once again for joining.